Hey everyone, welcome back to LearningHub. In this video, we're taking our understanding of probability to the next level by diving into the cumulative distribution function or CDF. If the probability distribution function or PDF tells us how dense probability is at each point, then the CDF shows us how that probability accumulates over time, like watching a glass fill up drop by drop. We'll explore what the CDF really means intuitively and mathematically, its core properties that make it a fundamental tool in probability theory, how it's related to the PDF, and how to use it to compute probabilities across intervals. Plus, we'll break down some key equations and even prove how PDF and CDF are interconnected using calculus and curve intuition. So, grab a notebook and let's make probability smooth, visual, and cumulative. Let's get started. Imagine you're slowly filling a glass of water. As time passes, the water level rises steadily, never going down, just filling up more and more. This rising water level is a great way to visualize the cumulative distribution function or CDF. Just like the water level tells you how much has been poured so far, the CDF tells you how much probability has been accumulated. That is, the probability that a random variable has taken on a value less than or equal to some number. Mathematically, for a continuous random variable x, we write fx equals to probability of x is less than or equal to x. This means fx gives you the probability that the value of x is less than or equal to some chosen value x. But where does this probability come from? It comes from the PDF, the probability density function, which tells us how probability is spread at every point. So, to calculate the CDF, we add up all the tiny probabilities from negative infinity up to x. That's done using an integral here. Here, ft is the PDF and t is just a placeholder or a dummy variable used for integration. So, in simpler terms, the CDF is the area under the curve from the far left up to the point x. It represents the total probability accumulated up to that value. Just like the glass keeps filling and never overflows beyond 1, the CDF is always increasing and stays between 0 and 1. And that's the heart of cumulative distribution function. It's not about where a probability is sharpest, but about how much probability has been gathered up to a certain point. Now that we know what the cumulative distribution function or CDF is, let's explore its core properties using math, real meaning, and a little bit of intuition. The first property is that the total probability is 1. This means the total probability that the random variable x lies anywhere on the number line is exactly 1. Think of it as the entire area under the PDF curve. It has to be added up to 100%. The second property is that the CDF at negative infinity is 0. This one is pretty intuitive. That's 0 probability that x is less than negative infinity because, well, nothing exists before that particular point. The third property is that CDF at a point A. This is a very definition of CDF. It gives you the probability that the random variable x is less than or equal to a specific value A. And the fourth property is the relationship between PDF and CDF, also called the derivative rule. This is a beautiful connection. The PDF is the derivative of the CDF. Why? Because the CDF is the total accumulated probability and PDF tells you how fast the accumulation is happening at the exact point x. So let's prove it. Start with this particular formula here. Then by the fundamental theorem of calculus, we get dfx by dx equals to fx. This proof shows how the area under the PDF curve goes up to x using the CDF and how taking the slope of that accumulated area gives us the PDF again. Full circle. These properties are not just mathematical facts. They give you insights into how probability flows and accumulates in the world of continuous random variable. We'll wrap this up with a powerful geometric idea, the area under the curve. Imagine you're looking at a small slice of the probability curve, just a tiny interval around some point, say A. Now, because that interval is so narrow, the curve doesn't really have much room to change shape. It stays almost flat. And when a curve is nearly flat, we can think of it like a straight horizontal line. So instead of calculating the exact area under the curve, we just draw a rectangle right at that particular point. The height of the rectangle is the value of the curve at that point, And the width is the tiny interval we're interested in. And there it is. The area of that rectangle gives us an excellent approximation of the probability over that narrow range. It's a neat trick. Zoom in close enough and even a curved function starts behaving like a straight line. That's why for small intervals we can use a rectangle to estimate the probability. Quick, intuitive, and surprisingly accurate. And that brings us to the end of our exploration of the cumulative distribution function, the CDF. We saw how it builds up probability like filling a container, how it connects with the PDF through integration and differentiation, and how even tiny intervals can reveal meaningful approximations through geometry. Understanding the CDF not only deepens your grasp of probability, but also sets the stage for powerful applications in statistics, data science, and beyond. Thanks for joining me on this journey, and as always, keep learning, keep exploring, and I'll see you in the next one.